Are they back? People went to the bathroom?
No, it's one girl. Well, I think we should start actually.
Okay, let's start then.
Do you want to close the door? Because is it? I think it's not noisy outside.
Okay.
But we have some kind of fresh air coming through otherwise.
For sure.
Okay. Shall we start? Yeah. So today is the second lecture in our mini course on some aspects of mathematical beauty. For those who missed the first one, we will put online the slides and the video, so you can recover it easily. And even if you missed something, you can always consult yourself with the online information. Yeah.
But we don't have yet a site where we can find these videos, right?
Not yet. It'll take some days. The person is doing the editing,
Okay.
and he said he'll need 1 more week. So maybe after vacation, after the holidays, yeah.
After the holidays, yeah, we'll have everything. So it's a team of professionals working on these films, not only philosophers but also filmmakers, editors.
Very fancy.
It's going to be a proper movie. Yeah. All right. I decided that in this lovely day, in this nice, beautiful weather, we should talk about beauty, mathematical beauty in particular. So let me start. The plan for today is to make some assumptions about beauty, what mathematical beauty is. It's a puzzling question. I mean, what the beautiful weather is, we kind of understand. What the beautiful painting is much more clear. What the beautiful music is kind of better understood. But what mathematical beauty is a hard question to answer. And I will start with some assumptions about what mathematical beauty could be, and I will make, as I think, an important distinction between perceptual and mathematical beauty. So, as you can guess, perceptual is something which you can perceive from a visualized mathematical entity. And mathematical beauty is something what mathematicians are keeping talking about mathematical elegance, about elegant proofs, beautiful theorems, something which we can't really draw or paint in colors, for example. So this is the most puzzling part. And I think this distinction is crucial for research on mathematical beauty. And then I will talk about symmetry, visible and invisible, hidden symmetries. You'll see what I mean later. And I will use a case study, as I said in my first introductory lecture. This course is actually about doing philosophical case studies in current mathematics. Okay. And my case study will be about a beautiful Peterson graph. I will show why it is beautiful at the end of the lecture, and then I will draw some conclusions. All right? So, my starting assumptions, let me just read it first of all. To judge something mathematical to be beautiful is to give it a positive aesthetic evaluation and to imply that this thing has the power to give aesthetic pleasure. So let's look a little bit closer to this sentence. I'm talking about judging something mathematical to be beautiful. So it's not about really postulating that there is a beauty in some things, but as I said, I'm doing philosophy of mathematical practice. I said it in the first lecture. So my approach is to see what mathematicians are saying about mathematical beauty. So I am concentrating about judgments about mathematical entities. When a mathematician is saying, oh, this is beautiful, he is judging something, right? It's not that I'm saying it is really beautiful, yeah? What I can see that some mathematicians, in some cases, make judgments about some mathematical entities. Right? And then they give a positive aesthetic evaluation. So it's evaluation, and it's positive. What I mean, it means that when they are saying, mathematicians are saying something is beautiful, they consider this entity in a positive scale, in a scale when something is positive and negative, and the beauty is a positive quality, they think. But they also imply that these objects have a power. They have some qualities maybe, but maybe a combination of them. But what is important, that this entity has a power to give them pleasure. So pleasure, it means that the judgment is not only evaluative, but also an emotional judgment, right? And also, beauty is a matter of degree. So usually mathematicians are saying that something is more beautiful than the other thing, and they compare, oh, this is a more beautiful proof, or this formula is more beautiful than the other one, or this is a more beautiful solution. So we have to be able to compare beautiful objects. We can judge one entity to be more beautiful than another, that's what I mean. Okay? Is it so far so good? Is it clear? All right. So with these assumptions, with these starting assumptions, I'm going to proceed and consider the case study. So a couple of words about this distinction between mathematical objects and their representations. I mentioned it in the first lecture that in mathematical practice, we take into account the fact that mathematicians are working with representations of mathematical objects. So, for communication and understanding, we often refer to a mathematical object with a visual representation using geometric, graphical, or symbolic elements along with definition. So, of course, remember, mathematical objects, we take that they are abstract, right? But mathematicians are working with formulas and graphs and signs, and also they give definitions, right? But for our purposes, to consider the question of the problem of mathematical beauty, we need to concentrate in this distinction between mathematical object as an abstract object and visual representation as a physical object. Physical object, I really mean things, inks on the paper, and some mathematical models. They could be made of piece of paper or wood. You can find it at mathematical department. These interesting, beautiful models. So, this distinction must be clear for you from the very beginning, is it? Okay. This is one of the examples of a visual representation of mathematical object. Mathematical object the function y equals 3x plus 7, but there is also a cognitive, or I said cognitive or visual representation, the visible graph, or it could be also a written formula. Here is the written formula, and here is the graph of the function. Okay. So, since we have this distinction between representations and abstract mathematical objects, we can talk about perceptual and intellectual beauty, right? Because perceptual beauty can be found in visually pleasing representations of mathematical entities, constructions, visualizations, arrays of formulas. For perceptual beauty, it is not the mathematical content that causes the pleasure. Let me demonstrate this with some examples. So, these are visualization of a fractal in mathematics. Of course, what we can see is really beautiful. We like the colors, we like the shapes, we like the repetition of the same pattern, how it grows. It looks beautiful, but we may not know what it is. This is another example. We like the colors and the shapes. This is a graph of a free group, but we don't know what it is. Even if we don't know, we can find it perceptually pleasing. Right. Platonic solids are considered ones of the most beautiful objects in mathematics. And here, I just took a page from with a list of a bunch of drawings and formulas as well. So you can see that some shapes are really smooth and nice and nicely curved. So these could be pleasing for us, even if we don't know what it is about. This looks beautiful, isn't it? Even if we don't see what are the bricks of this pyramid, and the bricks are numbers, and even if we don't consider the pattern, how these numbers are organized, it looks pretty, right? Here is the spiral, in these pictures somebody organized the composition. Somebody took two of them, put them together, and arranged kind of a nice pattern, something like a heart or something like that. Yeah. So the idea is, what I'm trying to demonstrate to you is that there are some beautiful visualizations in mathematics. There is a website where you can see more of them, and some of them look really, really attractive, don't they? Because of the colors, because of the structure, because of the smoothness of lines, and so on. But what I want to stress here is that for us, for appreciating the perceptual beauty, it's not necessary to understand what it is about. Okay. But when we talk about intellectual beauty or mathematical beauty, a judgment of intellectual beauty is about mathematical content. So now it's important what this drawing is about. And I'm going to use the example from ancient Greek mathematics, the Pythagoras theorem. The argument is visual, nevertheless, it is not so much perceptually and intellectually pleasing. It's not so much perceptually as intellectually pleasing. Yeah? So, if you consider, of course, it looks nice, it looks pretty, but what is more important for us is that when we understand, when we look at the argument, how it goes, we have two squares, this one, two big squares, yeah? We can see that they have the same size, because the side is A plus B here, and now we see, here is 1, here is 2, here is 1, here is 2, here is 3 and 4, 3 and 4 here, yeah, the purple triangles. So we can see that the area, the white area on the left-hand side square, A squared plus B squared, must be equal to C squared. Yeah? Is this clear? I hope. So the beauty of the argument is that you can so quickly, in such a simple way, prove a theorem. And here, of course, it's important to understand how the argument is going. So now we have a question. Given that we have perceptual and intellectual beauty, how does perceptual beauty of a visual representation interact with intellectual beauty? When we have one picture, for example, the Pythagoras argument, how the perceptual properties of this diagram interact with the intellectual mathematical beauty? This is a philosophical question. And I'm trying to answer this question. So, my approach is, first, consider a property which has traditionally been associated with beauty. And I think this property could be symmetry. Second, distinguish between geometrical and combinatorial symmetry. I will explain later what it means. See how geometrical and combinatorial symmetries contribute to beauty, and see how other features of visual representations contribute to beauty. Yeah? So far, so good. So let me start with symmetry. Symmetry, as we see it from Greek, symmetria is an agreement in dimension due to proportion and arrangement. And here is a quote from Pascal as well. Symmetry is what we see at a glance, based on the fact that there is no reason for any difference. Maybe this is a little bit confusing, and maybe this is a difficulty of translation from French to English, but what he really means here is that, first of all, we grasp symmetry sort of very easily. We have quite a high sensitivity to symmetrical things. When we see them, when we see that something is symmetric, we really quickly grasp it. Oh, this is symmetrical. And how we understand that it's symmetrical? Because it's kind of, it has the repetition of the same pattern, or it doesn't change if you do something to this object. For example, when we look at this picture, it's clearly symmetrical. Even if it doesn't take for us a long time to say, oh, this is a symmetrical picture. But here is important for us to understand what symmetry is in mathematics. In mathematics, a symmetry is a mathematical object, of a mathematical object, is a transformation which leaves the object essentially unchanged and structure preserving bijection of the object into itself. Well, so as I said, in mathematics, it could be, I have to say that visualizable mathematical symmetries, some symmetries of mathematical objects can be perceived in a visual representation of it. Some cannot. For example, reflection, that's what we see easily. Yes, that's what this is a typical kind of symmetry which we can see and grasp from visualizations, including mathematical visualizations, and also rotation, right? So these objects, if we turn this snowflake, for example, to some degree, and this point will go to this point, the object won't change, right? Or same happened to the ball. If you rotate the ball a little bit, the structure of the pattern won't change. So this object is a symmetrical object. Yeah? And the symmetry is a rotational symmetry. Okay. So we have reflection, rotation, and these are visible symmetries. But now let me consider some mathematical objects, and in particular I'm going to move to graphs. Graphs, I mean from graph theory. In graph theory, a graph is made up of vertices or nodes, and the lines called edges and connected. So vertices are connected by edges. Yeah, you see what I mean? I will show you in a moment. A graph is a mathematical structure used to model pairwise relations between the objects. So here are the examples of graphs. Right. What is important? So you can see that graph contains vertices. These points are called vertices, right? And the vertices are connected by edges. What is important? That in graph theory you can draw graphs in different ways. So in this picture you can see the same graph, but four different drawings of the same graph. Can you figure out that it's the same graph? Well, these two are very easy, yeah? Don't you see? It doesn't matter that the edges are straight or curved. What is important is the connection of the vertices, right? So you can see that if you move this vertex outside of the triangle, yeah, you will have this kind of drawing, right? Of course, the length of the edges is also unimportant. Well, it may be important in some particular tasks. Yeah, sometimes when graphs have weight, edges have weight, so they must be. It's useful to make them proportional to some values, but in most of time it doesn't matter. So this is an amazing fact that you can take a graph, which is an algebraic object. It's an abstract object. Remember, a graph in a graph theory is an abstract object, and it's a model of some mathematical abstract relationships. Right? But we can draw it. And this is an amazing thing in mathematics. We can draw a graph, and we can draw it in different ways. So this is a great opportunity to study mathematical objects using visualizations. And this is very interesting for us, philosophers, to understand how mathematicians do this. So, how about symmetry? As I said, some symmetries are visible. They are called geometrical symmetries. So, reflection, rotation, also transformation, when you can just move an object from one place to another place. They are usually called geometrical symmetries. But in graph theory, a symmetry is a vertex permutation that preserves the structure of the graph. The structure here means adjacency, non-adjacency, and number of edges. Let me explain what it means. It just means that the vertices stay. Adjacency means how one vertex 1 is connected with vertex 2. And one non-adjacency means one is not connected to the vertex 6. Yes? So when we make a symmetrical transformation to our graph, it means that we preserve this structure. We have to keep the same number of vertices, the same number of edges, and we have to keep the adjacency and non-adjacency. So we have to preserve the connection, the previous connection between the vertices. Yeah. You see what I mean? So, and it's called permutation. Permutation or transformation. So, in terms of permutation, here is an example of a simple graph, and straight away you can see that it has a reflection symmetry, right? Reflection in respect to vertical axis. Yeah, you can flip the graph, and there is some rotational symmetry as well. And all these symmetries are called automorphisms, and they can be written down in this algebraic form. Yeah, let me quickly, it's very easy, it's not so complicated. Let me just explain what it means. So they say that there are actually 4 types of symmetries in this graph, 4 symmetries. Lambda 0 says that 1 stays unchanged, this vertex stays unchanged, 2 stays unchanged, 3 and 4 and 5 and 6, and all of them actually stays unchanged. What does it mean? It actually means that we are not doing anything to our graph. It's so-called identity transformation. When we are talking about geometrical symmetries or something which we grasp intuitively, we wouldn't really grasp this kind of identity symmetry. You know, we wouldn't really think that it's this transformation as a transformation, yeah, because the object stays unchanged. However, in mathematics, as you can see, everything has to be fixed. So this is identity is the one symmetry. Lambda 1 goes into 8, 1 goes into 8, 2 goes into 7, 2 goes into 7, 3 and 4 and 5 and 6 stay unchanged. So what is it?
Reflection.
It's reflection, exactly, in respect to the vertical line. Lambda 2, 1, 2 stay unchanged, 1 and 2 stay unchanged, 7 and 8 stay unchanged, but 3 goes to 5 and 4 goes to 6. 4 goes to 6. What is this?
Reflection.
Again, reflection, but in respect to the horizontal axis. Right? And the final, 1 goes to 8, 2 goes to 7, 3 goes to 5, 4 goes to 6. What is this?
Rotation.
This is the rotation. Yeah. We just rotate our graph, which is kind of like a cross, and then the structure of the graph will be preserved. So these are all the symmetries of this graph. As you can see, not really all of them can be intuitively quickly grasped from the picture. For example, identity. Yeah, we have to be careful. So this is a graph theoretic interpretation of symmetry of graphs. I mentioned before geometric interpretation, and this is graph theoretic. It may also called combinatorial symmetries, because we are talking in terms of permutation, sort of changing positions of things. So combinatorics, geometry is about objects in space, roughly speaking. Yeah, of course I'm exaggerating, I'm making the picture extremely simple. So geometry is more about objects in space, and algebra or combinatorics is about how many things are in particular boxes, let's say, something like we have a number of boxes and we change and we can manipulate with these boxes somehow. Manipulate with symbols, if you think in terms of formalism. So here I was explaining everything on the picture, but in fact you can write down in this form, and brackets, you use brackets to show which object is exchanged with which object. So you can talk about symmetries simply in this symbolic